Swayam Prabha. Digital India. Educated India.
So first we will start with the discussion on bolts that are subjected to combined tension and shear force. So these are those bolts which are subjected to combined tension and shear. So we have an example here. Again, this example is taken from our textbook, which is N. Subramanian's book. This is a column ISHB 200 and ISMB 300 beam, which has an end plate connection with the column. Right? And here we can see that these three sets of bolts are provided. So basically 6 bolts are overall provided to join the end plate with the column flange. There is also some requirements for horizontal stiffener and diagonal stiffener. We will talk about them in a minute. First, let's discuss the basic dimensions. So the column is ISHB 200, beam is ISMB 300. There is a moment demand of 120 kilonewton meter in this direction. There is an axial force demand, which is marked as H, that is 20 kilonewton, and there is a shear force demand of 120 kilonewton. Additional information is provided. These bolts are high strength friction grip bolts, M20 size, and they are joining a 20 millimeter thick end plate. So this end plate thickness is 20 millimeter. The factored shear force and bending moment in the hogging direction and the axial force, they are also given here. Also, some more relevant details are given here. This beam size was ISMB 300, so total beam depth was 300 millimeters, and an end plate of 405 millimeter depth and 180 millimeter width and 20 millimeter thickness has been provided. 6 bolts are located on this end plate as shown here. So the distance of the top layer of bolts from the edge is 50 millimeters. Then the second layer is 85 millimeters away from the first layer, and then the third layer is 200 millimeters away from the second layer. These are those distances that are marked, and the remaining distance is 70 millimeters from the bottom edge. The relative distances of these with respect to the flange of the beam are also given. So the top flange of the beam is in between, is at the center of the distance between the top layer of the bolts and the second layer of the bolts. So now we can start calculating some distances. The beam bottom flange width is 140 millimeters. We are assuming that the pivot point will be right at the center of the bottom flange. So this will be the location of the bottom flange. Bottom flange thickness is 13.1 millimeters that we can look up in the catalog to find out what is the cross-section dimensions of ISMB 300, which is given as 13.1 millimeters. So basically from the bottom of the beam, the centroid or center of gravity of this reaction would be 13.1 millimeters. Then that point onwards, we would have bolt forces increasing proportionally, theoretically speaking. However, since we know that there is a possibility of flexible behavior in the end plate, we can approximate it as that these F1 or F2 are not actually exactly be proportional to the distance from the pivot point, but they will be equal. And one simplifying way to handle that problem is to assume that they are both acting at the location of the top flange. So wherever the top flange is, we'll assume that that's where both F1 and F2 are acting. Okay, and they are both equal. So that is a simplifying assumption we can make to account for some level of flexibility in the end plate. And then we can start balancing the forces. So first let's start to balance or try to balance the moment components. So it's easy to calculate the moment components about a force whose values we don't know. So we don't know the amount of compression that is acting here. So let's start to do that. We'll calculate the moments about this point. What are the total components that are acting, force components, which will introduce moment? First of all, there is a externally applied force at the centroid of the beam, which is the value is given 20 kilonewtons. So that will be inserting a force. That moment will be equal to force multiplied by the distance from the pivot point. So that force is 20 kilonewton multiplied by the distance, and that distance is beam depth divided by 2 minus the flange thickness divided by 2. So that makes sense. So this will be the lever arm. That is what this distance is. So this is multiplied and we will get a clockwise moment at the pivot point because of this force. The other component that we should account for is the actual moment that is applied, and that moment is 120 kilonewton meter. So that gets added directly since I am using kilonewton millimeter as the units in this formula. So let me use 10 to the power 3 to convert this from kilonewton meter to kilonewton millimeter. Okay, and both of them are in clockwise direction, therefore an addition sign, plus sign. Now these have to be balanced by the internal forces, and the internal moments, and internal moments are produced by these F1, F2, F3 forces. So as I had just mentioned, I have assumed that F1 and F2 are equal in magnitude and are acting at the location which is in the middle of the two forces, which coincides with the top flange centroid. So, and since there are two bolts at each layer, there are two F1s and two F2s. So we will do 2F1 plus 2F2. Right? So we are adding these forces multiplied by the lever arm, and the lever arm would be basically the distance from the bottom flange centroid to the top flange centroid, which is equal to 300 minus 13.1. So this gives the moment because of the first two layers of bolts. The third layer of bolt again is at a distance of 63.45 millimeters from the pivot point that has been calculated based on the dimensions that were given, and 2F3 multiplied by 63.45 would be the moment contribution coming from the third layer of bolts. So this is a simple equation. We have got three unknowns, F1, F2 and F3 here. We need to substitute them in some values for them so that we can get a single equation with a single unknown. So the straightforward method to do that would be to use the assumption between F1 and F2. So we had assumed F1 is equal to F2, so I can substitute that here. So now I've got only two unknowns, F1 and F3. F1 and F3 can be related. By the way, this F1 is now acting here, and it is acting at a distance of 286.9 millimeters, which is basically the distance between the centroid of the top flange and the centroid of the bottom flange. So I can say that F3 divided by its distance from the pivot point, with assuming that the plane sections remain plane, will be equal to F1 divided by 286.9, right? And now I can substitute that here. This value goes onto that side, 3.45. Now my F3 value can be substituted here to again write the entire equation in the form of F1. That's what we do. We write that equation in the form of F1 and we can calculate for F1, which turns out to be 104.5 kilonewton. F2 is also the same. So F1 and F2 are both 104.5 kilonewton, and F3 is much smaller than that, which is equal to 23.11 kilonewton. Okay. Now, if we do a force balance, we can also calculate how much reaction would be acting at the bottom flange of the beam. How do we do that? We know the forces that are acting externally, 20 kilonewton in this direction. Then these bolts are pulling the plate back in. Both of them are 104, and there are two of them, 104.5 and two of them. Then at the second layer also 104.5 multiplied by 2. Then at a 63 millimeter distance from the bottom, we have another one which is equal to 23.11 multiplied by 2. So for these forces, we can calculate how much will be the force at the bottom end, right? And that's what we can calculate basically by balancing all these forces. So we add all the bolt forces and subtract the external force that we are applying, and we get the reaction at the bottom flange. Now, having done that, now we should calculate what is the shear force demand on each of these bolts, and then we should look for whether these bolts are safe under these loading conditions or not. So here we can see that there are total 6 bolts Out of these, the first layer and second layer is subjected to largest axial force demand because of the bending moment that was acting primarily, and the third layer was subjected to a very small axial force demand. When it comes to shear force demand, all these bolts can be assumed to resisting the same amount of load, right? If we can assume that this plate is almost rigid in its plane, then that assumption is not such a bad assumption. So obviously now we know from this understanding that shear force demand is same in all the bolts, and these bolts are subjected to largest axial force demand. Therefore, the total um, force, the net force on these bolts is much higher than these bolts. Therefore, we need to worry about the design of these pair of bolts rather than this layer. If we are designing this bolt particularly, we have to be also mindful of the possibility of a prying action developing, right? Where we can imagine that as this top flange is pulling away from this point, this end plate may deform like so. And if it does deform like this, it will introduce an additional force Q that we had discussed in the very first week of lectures, that this additional force Q represents a prying action force which results in an additional force demand in the bolt, right? So this top layer of the bolt is likely to be subjected to an additional axial force demand, tension force demand, and let's first calculate that. So if we do that calculation, I have not shown the calculation here because we have done enough examples before. We can calculate that force, and that turns out to be 25.38 kilonewton because this plate was stiff enough. It did not introduce a very large prying force. We need to add that force to the force that we had calculated directly from the moment and which had been calculated as 104 kilonewton. So added together, the total force in the bolt becomes 129.88 kilonewton. Okay. The shear force demand, as I had mentioned, would be equally distributed among the 6 bolts that are present. Total shear force is 120 kilonewtons, and therefore the shear force demand in each bolt is calculated as 20 kilonewton. Now this part I am not doing again here, but basically we can easily calculate the tension capacity of the bolts that were provided here. I have given the details. These are HSFG, high strength friction grip bolts. Tension capacity can be calculated and shear capacity can be calculated based on the material properties provided. So if let's say we have calculated those, now we need to check whether these bolts are are safe under a combined axial tension and shear. For that, this interaction equation we would use, we have discussed that also, the shear force demand divided by the shear capacity and tension force demand divided by the tension force capacity, and their squares should be less than or equal to 1. We substitute the values here. These are already the design capacities, right? So the factors of safety are already inbuilt in these values. Once we do that, we'll get a value of 0.99, which is just less than 1, but that still makes still ensures that the bolts are safe under the combined axial force and shear capacity, shear demand. Now I have a question. Let's say in this case, the bolts turned out to be just safe to be able to resist the moment demand. There was a moment demand, and this bolt we found was carrying the largest amount of force, and it was just barely safe. We got a factor of safety of 0.99 instead of with an upper limit of 1. Let's say if they were not really safe and it had fallen short by, let's say, 20%. So that factor, instead of 0.99, let's say we had got 0.8. Then would it have been wise to provide additional welds between the end plate and the column flange to resist the same force? So basically these bolts are participating. These bolts are going into tension to resist the force and also shear to resist the applied force. And let's say we are finding that that is falling short a little bit and we don't want to drill another set of holes. So let's say these designs were done and there was some miscalculation. We had, let's say, ignored the prying action. And when we do a recalculation at that, by that time, these holes have been drilled, the material has been supplied to the site, and we realize that the connection is unsafe by a small fraction. Now, can we just add two welds? Sorry, the welds can we add welds between the end plate and the column flange at site, and let's say we do enough number of welds so that it fulfills or it fills that deficit in the capacity. Would that be a wise choice? I'll give you a few seconds to think about it. Okay. So I hope you have made up your mind. You have an answer in your mind. The correct answer is no. That would not have been a good choice. In fact, not a wise choice. The reason for that is that we should never mix bolts and welds to resist the same load. So these bolts were supposed to resist this bending moment and combined bending moment, shear force, and this axial force. Either we should completely rely on bolted connections, same types of bolts, or we should completely rely on the welded connection. We should not mix them together. The reason for that is that they have very different stiffnesses. In fact, welds have much higher stiffness than bolts. And if we provide welds along with bolts, when we apply this force, most of the force will be taken or will be resisted by the welds in the beginning, and bolts will not be resisting any force, because for the bolts to start resisting some force, they need more elastic deformation. So what would happen eventually is that first all the force will be resisted by the welds, and welds will be highly stressed, and bolts will not be participating. And if the welds are not designed to resist the entire load on their own, they will fail at some point. Once they fail, they will not be able to offer any resistance, and the entire load will then fall on the bolts. So the bolts and welds will not work together, right? They are often provided at the same time in a single connection. For example, here you may see that we will discuss this also in a minute, that this beam is welded to the end plate using welds, but at the same time the end plate is welded to the column using bolts. That is perfectly okay, because then they are transferring different amounts or different types of forces, right? They are not participating to resist the same force. They are not sharing the same force among each other, and that's why that is perfectly okay. I hope you got the answer. So now let us also check whether the end plate has sufficient strength to resist the bending moment that will be acting at this interface because of this pull force. So we all know that this bolt, top bolt, will be subjected to the maximum tension force of 129 kilonewton, which is because of the prying action. The force in this top flange will be, we can say that it's 129 minus the prying action. So that is the actual net force demand, but some of it will be enhanced because of the prying action at this edge. So if we can zoom into this area, into this zone, let's see, this is the top most edge of the end plate, and the end plate is being pushed this way through prying action. Okay, and that force we had calculated, that had turned out to be 25.38 kilonewton. Okay. Next comes the point where the bolt is present, and the bolt is basically trying to pull the plate back in with a total force of, this is the top layer of the bolt, therefore the total force is 129.88 kilonewton. And further down, this is somewhere where the actual weld exists. So we can approximate the location of the weld. If we knew the size of the weld, we could have actually calculated the toe of the weld, but here, since we have not calculated the weld size, let us take the location of the bottom flange itself, and let's try to calculate the moment demand there in the plate. So let's take that location, and that is where some force is acting, which is actually the demand. Now we need to calculate the moment demand in this plate at this location. So first let's calculate these relative distances. So it has been calculated the distance of the top bolt. So the top bolt is this bolt from the weld. This distance is equal to 30 millimeters, and the distance of the edge of the plate from the location of the weld. So basically the edge of the plate to the bolt is 50 millimeters, that was given to us before, and then another 30 millimeters is the distance from the bolt to the top flange, and therefore the total distance from here to here will become 80 millimeters. Okay, so now if we know these lever arms, we can calculate the moment demand here. The moment demand here at this point of interest would be, at the toe of the weld, will be equal to 129.88 kilonewton multiplied by 30 that is the lever arm, minus 25.38 kilonewton, that is this force, multiplied by 80. Okay? And that gives us a total moment demand of 1877 Newton meter. Okay? Here you may notice that I have changed the units from the units in this expression was kilonewton millimeter, and if I change the units from kilonewton millimeter to Newton meter, I don't have to do any multiplication or division. The value would remain the same. Now this is the total moment demand at that location in the end plate. So this end plate should be able to resist this much of moment. So since it's a plastic design, we can this is a ductile system, so we can design this plate for the plastic moment capacity. It's a compact section, of course, it's just a plate. So if we look at this cross section of this plate and try to calculate its plastic section modulus, for this section the plastic section modulus will be calculated with the assumption that half of the cross section goes into tension complete yielding and half of the cross section goes into yielding in complete compression. And in such a situation, the net forces will be acting at these locations, which are the centroids of the each half, and the moment capacity, or we can say section modulus, section plastic modulus, would be equal to the areas of each half, so which is basically the thickness of the plate multiplied by the width of the plate divided by 2, area of that half multiplied by the lever arm, that is the distance between these two arrows, and that distance is nothing but T divided by 2 again. So basically the plastic section modulus can be calculated as W T square divided by 4. Okay, so that is plastic section modulus. If we multiply plastic section modulus with the yield stress of the material, we can calculate the moment capacity of this plate. So we do that, we take the plastic section modulus that we have just calculated, multiplied with the yield stress of the plate, dividing by the factor of safety for resistance in yield conditions, so that is 1.1. When we do that, here the width of the plate is taken as 180 millimeters, thickness was taken as 20 millimeters, and Fy is taken as 250 MPa, and then we substitute these values. We substitute these values to calculate the moment capacity of the plate as 2045 Newton meter, which is greater than the demand of 1877. Therefore, the plate is found to be safe in bending. So far we have checked the safety of the bolts and the safety of the end plate itself. Now let us also check the design of the welds that connect the beam to the end plate. Okay. These are going to be fillet weld joint, which is typically shop welded. So here in this diagram you can see this is the end plate, this is the beam, and the edges of the beam will be fillet welded with the end plate. And if we can look closely, these are the locations where we'll be providing the fillet welds. So typically we will discontinue it between the shear and the portion of the weld which is going to resist the shear force, and the portion of the weld which is going to resist the axial force. So again, to reiterate the total force demands, the shear force demand which is in this direction, the axial force demand which is in out of the plane direction, and total moment demand which is going to introduce tension in this fillet in out of plane direction. We need to calculate the weld size which will fulfill the requirements of these loads. So we will start with an assumption that the weld size is unit. So that our calculations are easy, and we will calculate the weld size which would be sufficient to resist this load. Some of the member dimensions are also listed here: the thickness of the flange for the column, thickness of the flange, thickness of width of the flange, and so on. We will refer to them whenever we need. Also, one idea that we have to implement here is that the axial force or the effect of the bending moment will be resisted only by the welds which are provided around the flange, whereas the welds which are provided along the web will only partially resist the moment. However, shear force will not be resisted by the welds around the flange. Okay, and the reason for that is that if we assume that these welds are resisting shear, that would also include an assumption that this flange has high stiffness in out of plane direction, which is not really the case, and therefore we cannot count on their ability to resist shear. So most likely the shear will be resisted by the welds which are provided along the web. Okay. So to start the calculation, let us first try to calculate the total length of the weld, and since we are assuming that the weld size is unit to start with, the length will also be same as the area of the weld. By the way, here there is a minor mistake here. This dimension 300 that is marked here is actually the beam size. It is not up to here. This is 300 millimeters from the top of the beam to the bottom of the beam. Okay. Now area of the weld, the middle portion of the weld, I am assuming it to be 240 millimeters long. That is another minor correction here. This is 240 millimeters long weld in the middle. Okay, and the end welds are of course all the way around the flange, and they stop because of the web in between. Okay, now with these corrections, let's continue the discussion. So area of the weld can be calculated as 140 is the width of the flange, so 140 at both ends, 140 multiplied by 2 plus this much of width of the flange, which is 140 minus 7.7, which is the thickness of the web of the beam. So that we will deduct, and the remaining we will keep that, again, two of those, sorry, that much length multiplied by 2, and then whatever is the additional at around the web, on both sides of the web, which is 240 multiplied by 2. So the total area of the weld for a unit size weld is 1024 millimeters square. What is the moment of inertia of these welds? So for the moment of inertia, we can calculate easily. This is a symmetric weld about this axis. We'll call it x axis. About this axis, we can calculate the moment of inertia. By the way, we are ignoring the part of the weld which is around the toe, around this fillet in the beam. Okay? We are assuming that it is, even though it is coming up to here, we are ignoring that part. Moment of inertia will be equal to, first we will calculate the moment of inertia of the top edge of this weld, which will be 140 is the length or the area multiplied by the distance squared, and distance from the centroid to this is equal to the half of the depth of the beam, that is 150 squared. So a r square plus the same thing would be repeated for the second layer, which is this layer. So the area there is, or the length there is, slightly less than 140 because of the beam web being present there, multiplied by the distance. So this time the distance is not 150 but 150 minus the thickness of the flange, that is 13.1 millimeters. So when we deduct that, we get 136.9 squared. So now we have calculated the moment of inertia of the top line and the second line of the weld. Now we will calculate the moment of inertia of the web portion. So moment of inertia of the web portion will be equal to bh cube by 12. That is the typical formula we use. So in this particular case, the h is 240, b is 1, but there are two such welds, so therefore we multiply with 2 divided by 12. B is 1 because we are assuming a unit size weld, and calculating this value, we get a moment of inertia of 13.56 into 10 to the power 6 millimeter to the power 4. Now we have calculated the cross-sectional properties of the weld. We can go ahead with the force calculation. So first, let's calculate the force demand in maximum force demand in any part of the weld because of the moment. So maximum force would be equal to, generally for stress we do my by I, right? M multiplied by y divided by I. So m divided by I multiplied by, we will do a multiplication with y, which will correspond to the distance. So m moment demand is 120 into 10 to the power 6 Newton millimeters. multiplied by y. Y is 150 from the neutral axis for the extreme fiber of the weld. That is 150 divided by I. I is this value that we have just calculated. And from there we get the force demand on unit length of the weld as 1327 Newton per millimeter. Now the force demand will increase as the size of the weld increases. Sorry, force demand will decrease as the size of the weld increases. Now, similarly, the force due to the axial force we can calculate. Um, the axial force given is 20 kilonewton, which is acting in out of the plane direction. So it is out of the plane direction. We will take 20 into 10 power 3 newtons divided by the total area, because we can assume that the entire cross section of the weld or the beam is participating to resist the axial load. So that gives me a force demand of 19.53 Newton per millimeter length. Force due to shear force. Now, because of the shear force, we are assuming that only the middle portion of the weld is participating, which is around the web, and therefore we will take only the cross section area of that portion. So the total shear force demand was 120 kilonewton, which was given here. That divided by the length of the weld, that is 240 multiplied by 2, that gives me a force demand of 250 Newton per millimeter length in the fillet. Now we need to be careful while designing it. So we are assuming that this part of the fillet is not resisting any of the shear force which was acting in the vertical direction. However, this fillet will be resisting the moment effect, and it will also be resisting the direct axial force effect, which is acting in out of the plane direction. So, but both of those moment and axial force will have the same consequence on the weld, if we can think about it. So the force component, because of them, will be in the same direction, and therefore we can directly add the two forces. So the force demand because of the moment is 1327 Newton per millimeter, and the force demand due to the axial force is 19.53 Newton per millimeter. We can add them and we get the total force demand on the extreme weld. Now that is of course likely to be the maximum force demand anywhere in the weld, but we should be careful that we did not account for the shear force here, but there is a portion of the weld which is resisting shear force as well as the bending moment, and for that portion we should check again whether the moment demand, the force demand there is higher than what we have calculated here. So for that portion, let us calculate the force demand for this portion. So in this case, here we had calculated the force demand to be 1327, which was the extreme fiber, and the neutral axis is right in the middle. So here at this location, the force demand will be proportional to the distance from the neutral axis. So we can simply say 1327, that was the force demand in the extreme location, multiplied by 120, which is the location of this point, divided by 150, which was the location of the first point, extreme point. Okay, so if we do that, we will get the force demand at the top end of the web weld. Plus there is an effect of the axial force, which is 19.53, which we had calculated for the earlier weld also. That will be true here. So these two can be added directly because they have a resultant force in the same direction. Plus the effect of the shear force we have calculated before. This is in this direction, in downward direction. The earlier two forces were in the out of the plane direction. Now they are at 90 degree from each other, so we have to take the resultant by vector multiplication, uh, uh, by resolving the components in the two directions. And what we find is that that force squared plus the out of the plane force squared, that should give us the total force demand, which is calculated as 1109 Newton per millimeter. Now we can compare between the extreme weld and the weld at the top of the web. So the extreme weld was subjected to a force demand of 1346, whereas this weld is only subjected to a force demand of 1109. So therefore the extreme weld is more critical, and let us design for that. So we can calculate the weld size by simply using the expression which is available, which we have discussed again in the past. For a fillet weld, we will take the FU value. For a fillet weld, we don't use the FY value, but we use the FU, the ultimate stress of the parent material as well as the weld material. And typically, the parent metal is the weaker of the two, therefore we take the Fu value of the parent metal, then we divide by √3 to correspond to the shear mode of failure. 0.7 here represents the throat thickness. So this gives us the total area, and then we can calculate the size of the weld by this expression, wherein the total force demand divided by the force demand of a unit weld, unit size weld, which will give us the total force demand. And we are using a factor of safety of 1.25 here because this is typically a shop welded joint. And then we get the weld size of 10.15 millimeter. So we can provide an 11 millimeter or 12 millimeter weld, and that should suffice in such a scenario. The question arises, if we look at this web of the beam, the components that this weld is going to join are as follows. There is an end plate that has a thickness of 20 millimeter. Then there is a flange of the beam which has a thickness of 13 millimeter. And then there is also, in this case here I can show, this is the web which only has a thickness of 7.7 millimeter. So now for the weld that is joining these two components 20 and this one is 13.1, or a weld that is joining two components, one of the which is 20 and the other one is 7.7. Can we use an 11 millimeter weld for joining these kind of components? Think about it. Is it okay to have a is it okay to have a weld, a 10 millimeter weld, which is welded to only a 7 millimeter thick plate? Is there a problem with that? It is not a problem. Actually, some of you may recall that, or might be trying to use the condition for fillet welds, wherein we were welding two plates together, let's say, and we were required to provide a fillet weld here. And the requirement was that if it is a square cut surface, we should leave at least 1.4 or 1.5 millimeter exposed. That means the weld had to be smaller than the plate thickness, right? Similarly, there was a requirement for a curved toe also, right? Both of them insisted that the weld should be smaller than the thickness of the plate by a certain amount at least. Here, that condition does not apply because we are not really welding the edge of a plate. Instead, what we are doing here is that edge of the plate is already at this end, and the edge of the plate is already touching the other plate. And what we are doing here is that this side, here there is no such restriction that the weld has to be thinner than the plate thickness. The weld can be thicker than the plate thickness, which is perfectly acceptable, and we can weld it this way. So now in this connection, we have discussed how to design this weld which is between the beam and the end plate, welds here, here and in between, how to design the end plate itself for the moment capacity, and then how to design the bolts. Now the question comes about the designing of this column, whether any special provisions have to be done to make the column resist this load effectively, right? And generally, of course, when we have a shear force demand, we should this shear force demand would be calculated using StatPro itself or any analysis software that you are using. That software will give you the shear demand, and that column should be designed for that shear force demand. However, in addition to that, if these local forces may not be accurately calculated, and the shear force demand may not be exactly accurate if you use the values calculated using only a software which assumes a center line as representative of the member size. In such a situation, we should again do a hand calculation to calculate the shear force demand on this member, and then make a provision for appropriate stiffeners or doubler plate to resist that moment. In addition to that, any local stresses that develop in the web because of this concentrated forces coming out of the flange of the beam, for such things we can always utilize the provisions for plate girders, right? Since plate girders are not really a part of within the scope of this course, I will not spend much time discussing this. I would recommend you to go through clause number 8.7 to understand the requirements of these stiffener design, etc. And we can have a separate discussion on that later on. But I would skip that discussion for this course, and that would conclude basically, as far as this course is concerned, the designing of an end plate type of a connection.